Okay, thanks. So let's start. So, okay, Bayesian surrogate analysis. So this goes a step back from what you've seen in the previous talk. So Katharina used surrogate models to do sensitivity analysis and classification. And I would like today to talk a bit more about these surrogates. And I will use them for uncertainty propagation, which is very similar to the sensitivity analysis. So at the center of our problem, we have some computer simulation that, so in my applications, that typically a fluid dynamics simulation or a structural analysis where we have some uncertain input variables that, for example, could be an unknown fluid viscosity or an unknown elastic modulus. And now we want to propagate the uncertainty in these input variables through the simulation to our output where we have some uncertain observable C at some measurement site or location X. Could be a shear stress or a strain. Now, the basic equation that we need to solve, it's very easy. So we want to describe the uncertainty or the probability of Z at location X, given some data. I will explain that later. And this is easily determined by this marginalization of the joint probability of the Cx and your A's. Now, it turns out for many practical problems, this is only possible via a so-called surrogate model. And I would now like to bring this into a bit of a context. So there's out there this handbook of uncertainty quantification with roughly 1,200 pages. And probably Katharina has used some tricks that are in this book. But I actually want to go a step back more into the fundamentals of what's happening here. And I want to write it down in a Bayesian way. So the basic problem, we have our simulation output Z and our simulation output A, and we want to solve this equation, the probability density function of Z, where we introduce via marginalization our input variables A. And for now, for a while, I will assume that this posterior for our input variables A is given. Now let's assume that this PDF of A, so this is determined by some experimental data, of course, here that has happened before the simulation. Now let's say that this looks something like this. So the PDF of A could look something like this, and we want to solve this integral equation. And in order to do that, we draw samples from our PDF and compute the simulation each. Now we could proceed and arrange this data in a diagram of Z versus A, where this crosses denotes the data. We could do that. And then we gather this data and arrange it into histograms and approximately infer our probability density function of Z. Now the problem here is that in many interesting applications, one evaluation of Z can take days or weeks or even more. So the conversions of this integral is really slow, and there's no way we can do this in a brute force way. But not all hope is lost. There is a workaround that we can use. That is, we construct a so-called surrogate model. So step one, we evaluate a few simulations, maybe a couple of hundred or maybe thousands, as many as we can afford. And then we could visualize that in a diagram of simulation output Z versus simulation output input A, similar to before, but we have much less data now. Now we construct this so-called surrogate model, which is just a fancy term for fitting a cheap function to this data. Then we replace our simulation with the surrogate and perform the inference at a reduced computation time. So what is important here is when the simulation takes days or weeks to compute, the surrogate model will take seconds, milliseconds, or microseconds. So this is how we make the inference possible or feasible. Now, but there's another question that could arise here. So the obvious weak point here of this approximation is that we don't really know how good this surrogate function is or how trustworthy is what I call it. And for this, I would like to pose two questions. The first one is, what is the uncertainty or the trustworthiness of this surrogate? because there is not just one plausible surrogate that we can fit to this simulation data, but there's actually an entire distribution of surrogates that we could use here. And which one should we use? Now, the second question is the choice of this particular surrogate up here will affect your simulation uncertainty in the end somehow. So how does this propagate? So I have introduced this problem, and I will walk you now through some equations that are at the core and the substance of my paper. So you remember the original equation that we want to solve, and we now cast this surrogate workaround into some mathematics. So we say that our simulation set can be approximated by a surrogate model, set surrogate, and I call this a function g, that is a function of our input variables a, and parameterized on some fitting parameters or regression parameters c. Now, generally, these regression parameters will depend on the measurement site where you measure your observable set. And the phi's are some basis functions. So I'm using this generalized linear model for most of the results that you will see here from now on. Now, okay, so we have defined the form of the surrogate model, and now we proceed to learn these regression coefficients, the fitting parameter c, from a small training data set. So capital A now is the set of samples or pivot points from our input parameter space, and capital Z is the set of corresponding observations or evaluations of the simulation, where we have this double index here for I for the sample corresponding to this I, and X for the location site if we have more than one. Okay, so we can gather this data into this joint set simulation data, DSIM. And we now, from this original equation, we arrive at this equation, and it looks a slightly bit different. So first of all, we now have these additional training data proposition around here, but also we have changed the background information here. And I denote this with this tilde here. So the background info I tilde here is not the same as the background info up here. And this is important because generally a probability of X conditioned on some background info is not the same as a probability of X conditioned on some slightly different background info. Okay, so let's look at this term around here. The probability for the sets given our input variable A and the simulation data. And we can quantify this easily by introducing our regression coefficient C's with marginalization. So all what we do is we introduce here the C's and marginalize with respect to the C's, and we find this expression. Now we can plug in this line into this term here, and what we find as a result is that our new probability density function for the sets is given by this lengthy and somewhat scary expression, where we marginalize not only with respect to our input parameters A, but also with respect to our regression parameters C. So this looks a bit scary now, but we will break it up into a few easy components. Right before we do that, we'll first show what some easy approximations that you can usually do is when we look at this term. So the probability of set given regression coefficients C and A, and we remember that we say it in I tilde, that we can say that set is approximated by this regression function T that is only determined by A and the C's. So that means that this expression here is just a delta function located at our surrogate model. Now we can insert this, so I simply plug in this delta instead of this probability here, and we arrive at at a slightly less scary equation here. Now we're still fine, or we still haven't really approximated anything, but now here comes what you usually would like to do. Yeah, you would like to look at this term here, the posterior probability for the regression coefficient C given your simulation data, D. And you would like to say that this can be approximated by a delta that is located at some optimal regression parameter set C star, yeah, where the C star is defined by some optimality criterion O that usually depends on the parameterization of your surrogate function and, of course, also the data. I'm not specifying that any further here because there's no need to. So let's assume we can approximate this term here with this delta here. Then we can plug that in and we find an easy result. So yeah, okay, I have done the marginalization with respect to A2 now, but we find that our probability for the simulation output set is approximately the probability density function for the sets as yielded by the optimal surrogate coefficients C star. So this is the common ground, what people usually do and what people usually would like to do. And I would like to point out a particular problem that can arise here sometimes. So sometimes this posterior for the C's is in fact not sharply peaked at some particular value. And that can happen if the data is little or uninformative, for example. So the problem is that sometimes your surrogate is not perfectly trustworthy, which is in contradiction to this assumption here. Yeah? By imposing that the PDF of C, given the data, is a delta, you effectively say that your surrogate is perfectly trustworthy, or the other way around, it has no uncertainty. So I would like to go a step back and look at this term here in a bit more detail, whether we can find something better for this expression. Can we quantify the surrogate uncertainty or trustworthiness, whatever you would like to call it? Now, before I proceed with some further equations, I would like to pose a possibly provocative statement where I distinguish between the naive uncertainty propagation, where we just find an optimal surrogate, and a Bayesian uncertainty propagation, where we include this surrogate uncertainty and marginalize over it accordingly. So you might disagree. I'm open for debate on this. So we are back at our equation that we need to solve. And now let's take a look at this quantity that I have talked before. So it's now not a delta. We want to make something better here, or something that describes the uncertainty of the surrogate. So we can just use Bayes' theorem to identify the likelihood here. So this would be the likelihood that we get from Bayes' theorem. And if you remember, so the capital set was the set of our simulation data, and the capital A was the pivot points or the samples in input parameter space. And so this is the likelihood for the simulation data. And if we don't know anything better, we might as well assume a Gaussian, because that has also some very convenient properties that we will see later. So yeah, this is the usual Gaussian likelihood, where this chi-square is the usual misfit term. And I'd like to talk very bit about this delta here. How can we explain this? So the simulations that I'm usually looking at are deterministic, and they have a very tiny numerical error. Yeah, so there's usually really machine precision and rounding errors and so on that we need to consider. So this delta possibly can also describe that, but this numerical uncertainty is actually insignificant for many applications. But you could also view it at it a bit differently, and you could say that this delta also covers the uncertainty of the surrogate itself, or the other way around, the trustworthiness. So this delta now quantifies the trustworthiness of my surrogate. Now, of course, we don't know this delta, yeah, so we need to marginalize, we need to integrate out delta, and we finally arrive at the posterior for our regression coefficient C, that is the well-known student t-distribution. Okay, so first things first, the evidence that's easily computed here. Of course, we can compute the evidence of the student t, and we find this scary, but for many of you familiar expression for the evidence. I'm not going to focus on that so much. Let's assume that we have chosen a particular surrogate model according to a model comparison based on these evidence values. Now, having chosen the surrogate model, what is the trustworthiness of this surrogate? So let's get back to our basic equation that we're talking about now for some 10 minutes or so. Again, from this posterior for the regression coefficient C's, we can compute the moments, and these are just the moments of the student t-distribution that are also very well known. So the first moment of the C's is this short expression where, okay, the M is a matrix composed of the basis functions phi that we had in our generalized linear model, evaluated at the samples or pivot points in parameter space, and then sampled into this matrix here. Now H is just M transpose times M, and Z was the data, so the expectation is just H inverse times M transpose times Z. Now this is very fine and nice, and this is the same result if we would have just assumed a perfectly trustworthy surrogate, which is fine here. But what's different now than with the perfectly trustworthy surrogate is that we also get an uncertainty on the estimate for our regression coefficient C. That is not zero now. And also here in this expression, we can identify this familiar term of the misfit. So this is the minimal misfit divided by the effective number of degrees of freedom, which is the Bayesian estimate for our surrogate trustworthiness delta squared that we introduced before. Now this is very nice, but until now we have only looked at this term here. But what we will actually want to do, we want to infer the uncertainties of the set. So having this part now, we actually want to solve this equation to come up with uncertainties for set. Now this turns out to be rather easy with what we have by now. So this first line is just a definition of the first moment of set. And we can, this first expression, this probability for set here, this is just what we had written down before. And we can use this delta functional to integrate with respect to set. So you know this trick probably. And we end up with the second line, where we remember that we have to substitute the set now for our surrogate function G. And this is the second line. And then we remember, okay, surrogate function G was this generalized linear model that we can just insert. And the regression coefficients C appear linearly, so we can just use the expectation of the C's that I had shown you before. Okay, so also this is all fine and well. And the same result if we would have just assumed a perfectly trustworthy surrogate. So the mean of the predictions from the simulations is still going to be the same. But again, we actually want to look at the uncertainty of these predictions. And for that, we again have to look at the second moment. So the first line is just, again, the definition of the second moment, where we have used the same trick again as here with the delta. So we can substitute Cx and Cx prime. Cx and Cx prime can substitute that for G and G prime. We can then plug in our generalized linear model again, and we find the expectation of this product here, which we can break up. We can identify into the square, or the square of the means plus our covariance matrix. Also, this formulation should be very similar. So this should familiar, pardon. So now, what is the difference if we would have just assumed a perfectly trustworthy surrogate? Is that this term disappears. Yeah? So if we assume that the surrogate is perfect and nice, so the probability for the C's, given our simulation data, is a delta, then this term vanishes. But if that's not the case, then we have this additional term here. Okay, so I'm having roughly 4 minutes. So I will go through this part here very briefly. Polynomial chaos expansions might be familiar, or for some of you. This is a special case of this formalism here, where we construct our basis functions phi such that they fulfill this particular orthonormality criterion. Now, the problem here is that this can be difficult to find a basis that fulfills this requirement for non-trivial posteriors of A. But the good side up is that this lengthy expression simplifies a tiny bit. But this is a price that you want to have to pay. Okay, so very briefly, what is the relationship to Gaussian process regression? So you remember our lengthy expression where we had inserted this delta here. We had assumed that Z is uniquely determined by our surrogate function G, given A and the C's. But for a Gaussian process, we could take a step back and say, okay, this is not unique, and we have an additional uncertainty where we say that this probability now is a Gaussian multivariate that is centered at the surrogate function with some covariance matrix K parameterized with some theta. Then, okay, so we just need to be aware that this covariance matrix K appears again in the posterior for the C's, and we just need to keep track. And we formally find the same results as before, but we just have to account for our additional correlations and account for this term in first moment, and similarly, we have to account for these familiar expressions in the second moment. Now, okay, this should, okay, so the immediate summary. So what we did is we ended up with a generalized linear model, or a Gaussian process, if you want to, is also possible, for the prediction where we marginalize our regression parameters. So that's the summary in one sentence. And I have now roughly 1 minute and 20 seconds to show you an example of some computer simulation where we apply this to. So everyone knows what is the human heart, and most of you will know what is the human aorta. And we are now looking at the computational fluid dynamics of the blood flow in this aorta. So to simulate this, we solve the Navier-Stokes equations that look for this problem like this. And here, eta is the viscosity, and the viscosity eta now is parameterized in some uncertain input parameters A, where we have this generalized power law for the non-Newtonian fluid model. Now we solve the set equations on this aorta-like domain that looks like this, and we measure the wall shear stress on some spot X, for example, here. So, oh yeah, and I forgot something. We didn't talk about this posterior for the experimental parameters A before that go into the simulation. Due to a lack of time, I will be very brief about this. With measurements of real human blood viscosity in this graph and this viscosity model and a Riemannian prior with a Gaussian likelihood with an unknown variance, we find that the posterior for the A's looks like this. So it's not super complicated, but it's also not trivial. And we don't want to construct a polynomial chaos basis for this. So this is my second to last slide now. We have all the ingredients now together to compute this example. And what you see here is the wall shear stress from this blood flow as a function of time. And the black dots are data as measured from a set of simulations. And the continuous solid line is the mean surrogate function. Now the blue shaded area is the uncertainty with the optimized C's, with the optimized surrogate, and the red shaded area is the uncertainty accounting for the surrogate uncertainty. And while over here it's perfectly fine to neglect surrogate uncertainty, over here this is a bit more questionable as the surrogate uncertainties take up a large portion of the total uncertainty. And in this particular example, the problem here was some backflows that made it difficult to find a good and trustworthy surrogate. So neglecting this can lead to overconfidence. So now I'm really done. The take-home message here is uncertainty propagation can sometimes be difficult if you want to do it brute force. So you will have to use a surrogate model. And finally, don't trust that surrogate model. And with this, I'd like to acknowledge Ali Mohammad Jafari, who has seen an early version of this manuscript and provided with me with some good comments, and also the funding from Graz University of Technology and my collaborators in the laboratory and in the computer simulations. Thank you.
Thank you very much.
And sorry for the overtime.
Yeah, would be less questions, sorry. So a quick question. I have a question, maybe I start. What about a surrogate then have a multimodal solution after the simulation? Is it a bad surrogate? So should I choose another surrogate, or can I deal with something like that?
So I assume the Gaussian likelihood for the simulation data. So you would only get a multimodal distribution for that if it's in the prior. But there's seldomly a reason to assume that in the prior. So in this particular case, it was a flat prior because there's no real information on these regression coefficients, what they could look like.
Okay, thank you.
But of course, there could be multimodality in the posterior for your input variables A, right? So yes. This is what I'm trying to address here. Yeah. So this is no problem if you just marginalize with respect to this multimodal posterior.
I hear quit.
Hi, can I ask a question?
Thank you. Yeah.
Yeah. Okay. Thank you for your talk. You just mentioned about the flat prior on slide 10, and that resulted in a student T distribution. But typically these deltas in your equation, I would regard them as scale parameters. And there is a school of Bayesian thought which says scale parameters should be modeled by Jeffreys priors. Of course,
yes, exactly. Thank you. It turns out that the Jeffreys priors for these C's is flat.
Say that again. I'm sorry, you're a bit difficult to hear.
The Jeffreys prior for these is flat.
No, I guess you misunderstood the question.
Okay.
For the delta, we use what is called Jeffreys prior 1 over delta.
Yeah. Okay.
That's the reason why later on you get chi squared divided by n minus 2 and
yeah.
The -2 results from this Jeffreys prior.
Yeah, thanks for clarifying that. Yeah, indeed, the prior for the delta is Jeffreys prior. Yes.
Okay, thank you.
I
Yes,
thought
yeah.
you were referring to the C's.
No, it was not that difficult. Thank you. Yeah.
Other questions? Something in the chat? Oh,
I would have one.
yes.
Sascha, thanks for the nice presentation. Have you already thought about going one step further? The a posteriori determination if the surrogate is good. So not only looking at the uncertainties, but actually computing how trustworthy the surrogate is?
Yes, sir. So there's in the paper there's a specific measure that I propose for this. Let me try and find the slide where I wrote it down. So how could you measure this surrogate trustworthiness? So I said before that, let me get my pointer, that if the surrogate is perfectly trustworthy, then this term here vanishes, right? So you could measure the surrogate trustworthiness by the ratio of this term marginalized with respect to the A's divided by this term marginalized with respect to the A's, or the total sum, if you will. So this would give you a proportion of the surrogate uncertainty as a fraction of the total uncertainty. This is what you could do here. But you can also inspect it visually in one of the later slides here. So here, for example, here you can see it already here. So you might be able to see this tiny shade of red here. So you can see the surrogate uncertainty is just a tiny bit more than the optimal surrogate. So it's really not far off from being perfect. But around here, by visual inspection, you could say it's maybe 30–40% or so. So yes, you can cast it into numbers. Absolutely.
Okay, thank you.
But this is just what I proposed. There might be different sensible measures of this trustworthiness.
Okay, I don't see any other questions. So thank you, the speaker, again.